Good evening, and welcome to Quiet Science. Tonight, we're going to slowly explore how scientists rebuild lost worlds from stone. Ancient shorelines, vanished seas, buried rivers, reefs, deserts, and ice-covered margins that no longer exist in the same form. We'll move gently through the clues left behind in rock layers, fossils, ripple marks, minerals, and magnetic traces, one idea at a time, with plenty of space to breathe between each one. Some of what we discover tonight will feel like quiet map-making across deep time. Continents drifting, seas advancing and retreating, old landscapes broken apart and patiently reassembled. But each clue is held in the earth itself, waiting in stone. If you'd like to join us for more nights like this one, you're welcome to like and subscribe below. But for now, get comfortable. Let your breathing slow. Let the ancient earth do the rest. Let's begin. Paleogeography begins with a quiet premise. Rocks keep fragments of former landscapes. Erosion wears those landscapes down. Burial presses them beneath younger layers. Plate motion carries them far from where they formed, and still some part remains. A beach may vanish, a river plain may sink, a reef may be lifted into dry country, yet the stone holds a portion of the older world. What once lay open to air or tide or current becomes scattered evidence, broken apart but not entirely lost. A modern continent is not a single untouched block of crust. It is a collage. Pieces have been welded together over long spans of time, and each piece carries part of an older geographic story. One tract of crust may preserve the remains of a shallow sea. Another may hold the debris of mountains that no longer stand. Another may have traveled from a different latitude altogether. The present arrangement looks continuous only because the seams have aged. Within the rocks, the older boundaries and journeys still persist. Sedimentary rocks are especially helpful in this work because they form in settings that have recognizable habits. Beaches sort sand under waves. River channels sweep gravel and sand along shifting paths. Lagoons gather quieter mud. Reefs build limestone in warm, shallow water. Dunes pile sand where wind keeps moving it. Deep seafloors receive finer settling material. Each setting leaves deposits with its own texture and structure, and those deposits can remain long after the setting itself has changed beyond recognition. Even a simple trait such as grain size begins to narrow the possibilities. Coarse gravel usually belongs to energetic water near steep sources, where strong flow can move heavy pieces. Fine mud often settles where motion is gentler, in lakes, lagoons, or offshore water. The difference between gravel and mud is already a difference in slope, in current, in depth, in distance from a source of sediment. A layer of stone carries within it a memory of how much force once passed through that place. The surfaces and internal patterns of rock add another level of memory. Ripple marks remain where moving water or waves once shaped loose sediment. Mud cracks mark wet ground that dries, shrinks, and opens to air. Raindrop pits preserve brief impacts on exposed surfaces. Crossbeds hold the inclined layers built by migrating dunes or currents. These structures are small, but they speak clearly. They show where sediment once met air, water, wind, and flow, and they do so with a directness that survives immense spans of time. Fossils deepen the setting. Corals suggest warm, shallow seas. Certain pollen suggests nearby forests. Burrows show that sediment once held oxygen and life enough for animals to move through it. Even when the body of an organism is gone, its presence can remain as a hint about water depth, salinity, temperature, or the conditions of the seafloor and shoreline. Life does not merely occupy a landscape, it records it. Chemistry contributes quieter signs. Some rock signatures indicate salinity, temperature, or strong evaporation. They help distinguish fresh water from brackish water, marine water from highly salty basins. These clues do not always announce themselves in bold forms. Often they rest in the composition of minerals or the balance of chemical traces. Yet they are part of the same landscape memory. A vanished body of water leaves not only shape and sediment, but also a chemical aftertaste in stone. Before any map can take form, the age of each rock layer must be constrained. A shoreline from one interval can be mistaken for a shoreline from another if the dates remain uncertain. Earth has repeated many settings. One place may have been dry land, then shallow sea, then dry land again. Sea level rises and falls many times, and the same region can preserve alternating records of shoreline, deeper water, exposed plain, and marine flooding. Without age, these repetitions blur together. Plate tectonics sets the broad stage beneath all of this. Crust moves across the globe. Sediments and fossils that were once neighbors can end up very far apart. Some rocks keep a faint directional record of Earth's magnetic field, and these magnetic traces help estimate the latitude where the rocks originally formed. Mountain building also shapes the story. Rising highlands shed sediment outward. Later erosion may wear those ranges down so thoroughly that only grains in younger basins remain to show that they ever stood there. Climate leaves its own firm handwriting. Ice, rivers, deserts, reefs, and wetlands each create deposits that can later be recognized in stone. Yet some evidence is absent from the beginning. Soft sediments erode easily. Oceanic crust is often recycled back into the mantle. Whole stretches of former geography disappear before they can be preserved. Because of that loss, no single clue is enough. Rock type, fossils, chemistry, structure, age, and tectonic position must overlap. Only where several lines of evidence settle together does an older landscape begin to emerge from the scattered pieces of the modern world. Rock successions are divided into layers and larger packages, and within those stacked bodies of sediment, one environment gives way upward or sideways to another. A bed of channel sand may pass into floodplain mud. Lagoonal deposits may be overlain by open marine limestone. A quiet sequence of fine sediment may be interrupted by coarser material brought in under stronger conditions. These changes matter because ancient geography is rarely fixed. It shifts. Water advances and retreats. Channels migrate. Shelves deepen or fill. The boundaries between settings move across the land and sea, and the rock record preserves those movements as a vertical and lateral arrangement of environments. Nearby outcrops are compared so that a sandstone in one place can be weighed against a mudstone or limestone in another. One cliff face may show only a local slice, too narrow to reveal the larger setting. Another exposure, some distance away, may preserve the continuation of the same interval under different conditions. By matching these pieces, a broader picture forms from separate remnants. The work depends on continuity that is partial, broken, and often interrupted, yet still meaningful. A single layer does not have to look identical everywhere. It may change character as the environment itself changes across space. When a beach deposit grades seaward into offshore mud, the transition gives an ancient coastline its orientation. The sandy belt belongs to shallower, more energetic water near land. Beyond it, finer mud settles where water is deeper and quieter. That gradual shift from one deposit into the other places land on one side and deeper sea on the other. The coastline is a zone of change, and the sediment expresses that change with a steady reduction in energy, grain size, and disturbance away from shore. Cross-bedded sand carries direction within it. Its tilted internal layers form as dunes migrate under wind or as currents move sediment along the bed of a river or shallow sea. By measuring those inclined surfaces, the movement of sand can be inferred toward a particular region. This does not produce a complete map by itself, but it gives motion to the landscape. Dunes no longer appear as static heaps, and channels become more than places where sand happened to accumulate. The rock begins to show where sediment was traveling, and therefore where higher ground, open water, or prevailing transport may have lain. Ripple marks are read for shape as well as presence. Symmetrical ripples often reflect wave motion, a back and forth stirring that belongs to water moved by oscillation. Asymmetrical ripples more often indicate a persistent current moving in one dominant direction. In this way, a surface of stone can preserve not only the fact that water was present, but something of the manner in which it moved. A broad, shallow marine shelf under waves leaves a different pattern from a channel with a steady flow. Small ridges in sediment become evidence for the character of motion across an ancient surface. Mud cracks place some surfaces firmly outside permanent deep water. wet sediment dries, shrinks, and opens into polygonal fractures when exposed repeatedly to air. Such cracking fits tidal flats, floodplains, or lake margins where water comes and goes, rather than a continuously submerged basin floor. A layer marked by mud cracks carries a rhythm of wetness and exposure. It speaks of intervals when water withdraws or evaporates enough for the surface to dry. That rhythm matters because it narrows the setting. It places the sediment within a fluctuating margin rather than an unbroken depth. Fossil shells must also be judged for whether they lived in place or were transported there. A storm can carry marine remains inland and blur the original setting. Shells lying where the organisms grew tell one story. Shells swept from elsewhere and deposited in a new bed tell another. The distinction is important because fossils can otherwise mislead the landscape. A marine shell in a non-marine deposit does not necessarily mean the sea occupied that exact spot in a quiet, lasting way. It may instead mark a pulse of transport, a brief rearrangement by energetic water. Tiny fossil species are especially useful because some lived only within narrow ranges of depth, salinity, or temperature. Their presence becomes a quiet marker of specific water conditions. Large features in the rock may show broad categories such as river, shore, or sea. But these smaller fossils refine the picture. They can suggest whether water was shallow or somewhat deeper, fully marine or influenced by fresh inflow, warm enough for one community and not another. Their scale is small, yet their environmental range can be precise, and that precision helps steady the map. Pollen and spores washed into sediment extend the landscape beyond the immediate outcrop. They reveal nearby vegetation and help outline wetlands, forests, or drier interiors. A deposit laid down in water may therefore preserve not only the conditions within the basin itself, but also hints of the land around it. Wind and runoff carry these tiny remains outward from their source. Once buried, they become part of the record. Through them, a lake margin can suggest the nature of the surrounding lowland, and a coastal deposit can hold traces of inland plant communities. Coal layers mark long-lived swampy lowlands where plant matter accumulates faster than it decays in waterlogged ground. Such layers indicate persistent wetness, low relief, and conditions that protect organic material from complete breakdown. A coal-bearing landscape is more than a place with plants. It is a place where standing water or saturated soil remains long enough and where decay is slowed enough for thick organic deposits to build. On a paleogeographic map, coal helps define broad lowlands, often near coasts or in basins where drainage and sedimentation allow swampy conditions to endure. Thick beds of salt or gypsum point towards strong evaporation in restricted basins. These are shallow water bodies cut off from full ocean circulation, where inflow and evaporation produce concentrated waters and mineral precipitation. Such deposits narrow the possibilities sharply. They suggest water that remains present but limited, renewed imperfectly, and subject to repeated concentration. The setting may hold marine influence, but not the open exchange of a broad ocean. It may be inland or marginal, but in either case it is restricted enough for salinity to rise beyond ordinary marine conditions. Limestone reefs trace former warm, sunlit marine shelves. Their distribution often marks broad, shallow platforms along the edges of ancient seas. Reefs require a particular combination of depth, light, and water conditions, so their presence helps define not only a point on the map, but an entire marine margin. A reef belt can indicate where clear, shallow water extended for a considerable distance. It can also help separate open shelf from deeper basin. The limestone body becomes part of the shape of the sea itself, preserving the place where marine life once built upward in warm water. Glacial scratches and poorly sorted debris indicate moving ice. Such evidence places cold conditions onto the map and can sometimes even suggest the direction in which ice flowed. The scratches are marks of contact and motion. The debris, mixed without the sorting typical of water transport, reflects the carrying power of ice. Where these occur, the landscape enters another climate entirely. Rivers and reefs fall away. In their place stand cold surfaces, grinding movement, and sediment released from ice with little regard for grain size. This evidence gives both climate and motion to ancient terrain. Red beds, stained by iron oxidation, often suggest well-aired continental settings, such as floodplains or deserts, rather than deep marine muds. Their color belongs to exposure and oxidation under conditions more open to air. They do not define one exact environment, but they help keep the reconstruction on landward ground. A red succession may belong to broad plains crossed by rivers, or to drier basins where oxidation remains strong. In either case, it tends away from the low oxygen quiet of deep marine settings. Color becomes part of environmental placement. Ancient river systems are reconstructed by following channel sands, floodplain muds, and gravel fans outward from older uplands toward lower basins. The river is preserved not as running water, but as a pattern of deposits linked by source, transport, and settling. Coarser material near uplift gives way downstream to finer sediment spread across plains and into receiving basins. When these parts are connected, the map gains drainage. Highlands begin to shed, basins begin to receive. The surface acquires slope and direction, and sediment pathways reveal where water likely moved across the vanished land. Conglomerates with large rounded pebbles signal energetic rivers or shorelines. The pebbles themselves can identify vanished highlands because their rock types may match older source terrains now eroded or displaced. A coarse deposit is therefore useful in two ways at once. It speaks of strong transport, enough to move substantial clasts, and it also preserves fragments of the source. Even if the upland has been worn down almost completely, pieces of it may remain in the conglomerate. The basin keeps a sample of the mountain that fed it, carried outward by water and buried beyond the reach of later erosion. Minerals within sand grains, especially durable ones, can be compared across regions to test whether separated basins once received sediment from the same source terrain. Sand is not only a measure of grain size and transport, it is also a mixture of mineral fragments with different resistance to weathering and travel. If distant deposits share a distinctive, durable mineral suite, that similarity can suggest a common upland source. In this way, separated basins may be linked across later faulting, burial, or erosion. The source landscape extends itself through the composition of the sediment it sheds. Volcanic ash layers spread widely from a single eruption and act as thin time stamps within sedimentary sequences. A narrow bed of ash in one basin can correspond to a similar ash bed far away, allowing distant sections to be aligned more confidently. The ash does not describe the local environment in the same way as ripple marks or fossils, but it fixes different local stories to the same moment. Two places that preserve unlike sediments may still be shown to belong to one shared interval. The timestamp steadies the reconstruction across space. Radiometric dating of ash or lava adds numerical ages to that alignment. Relative order from fossils and layered rock relationships becomes anchored more firmly when some beds carry dates. This matters because similar environments recur and because tectonic movement can place old and young rocks side by side in confusing ways. A numerical age does not solve every uncertainty, but it narrows the interval and helps keep shorelines, reefs, rivers, and evaporating basins within the correct slice of time. The map depends not only on place, but on the sequence of changing places through millions of years. Magnetic signatures in rocks can be compared with the known history of field reversals, helping narrow age ranges and original latitudes for some formations. The same faint record that hints at latitude can also contribute to timing when matched against reversal patterns. This is especially useful where other age controls are limited. The result is a landscape placed more securely on the globe. A reef belt may belong not only to a certain age, but also to a certain latitude. A glacial deposit may be checked against where cold conditions fit more plausibly. Magnetism joins age and geography. Once latitude is estimated, climate indicators can be tested against it. Tropical reefs, desert dunes, and glacial deposits each fit some latitudes better than others. The fit is not used alone, but as one more overlap among clues. If a reconstructed block lies at a latitude consistent with its reefs, the picture gains coherence. If glacial evidence occupies a position where cold conditions make sense, the map settles further. Latitude does not dictate every local environment, yet it places climate-sensitive deposits within a broader planetary arrangement. Faults and folds must be restored as much as possible because later deformation bends, breaks, and stacks rocks that were originally laid down more simply. A shoreline deposit may be overturned. A river sequence may be repeated by faulting. A basin may be compressed until its former width becomes difficult to recognize. The present geometry of the rocks is often not the geometry of deposition. To recover the older landscape, the later distortion has to be unwound as far as the evidence allows. Only then can the original relationships among environments begin to reappear. Terrains, crustal fragments with distinct histories are matched to likely neighbors by comparing fossils, ages, structures, and igneous activity. A continent assembled from many pieces cannot be understood as though all parts shared the same past. Some blocks carry faunas unlike those of adjacent regions. Some preserve a different sequence of events or a different pattern of magmatism. By comparing these traits, likely former neighbors can be recognized. The map grows not just by tracing environments within one block, but by fitting blocks together according to the histories they contain. Mountain belts on one continent can line up with belts on another when continents are reassembled. These alignments create long stitched seams across modern oceans. The same broad zone of deformation, uplift, and magmatic activity may continue from one present shoreline to another once the ocean between them is removed. Such continuity helps support a reconstructed arrangement of continental pieces. It also affects paleogeography directly because mountain belts shape drainage, sediment supply, and basin position. When the seam is restored, rivers, forelands, and marine margins can be placed in more sensible relation to one another. Seafloor spreading histories help rotate continents backward through time, though this works best for younger oceans because older ocean crust is commonly lost. The ocean floor is not preserved indefinitely. Much of it returns to the mantle, and with it goes a direct record of former ocean geometry. Where younger spreading histories remain, they help constrain how continental blocks move apart or back together. This does not replace the evidence in the continents themselves. It provides a broader framework in which the surviving fragments of coastlines, basins, and mountain belts can be arranged. Continental blocks are placed with the help of models, but the models are guided by field evidence rather than replacing it. The reconstruction must still answer to the rocks, to the reef limestones, the evaporite basins, the coal swamps, the glacial debris, the channel sands, the pollen, the ash layers, the folded belts. A model can test whether a configuration is coherent, whether pieces fit in time and space, whether motions are plausible. Yet the landscape remains grounded in physical traces carried by the crust itself. The map grows from stone outward. Shorelines are rarely drawn as single, crisp lines. Deltas, tidal flats, estuaries, and barrier systems create broad, shifting margins between land and sea. Sediment moves through these margins continuously. Water freshens and salts by degree. Exposure comes and goes with tide, storm, and shifting channels. A paleogeographic shoreline, therefore, often occupies a band rather than an edge. This matters because ancient geography is not composed of neat boundaries. It includes transitional ground, places where categories overlap, and where the rock record may preserve alternating signs and shallow water within short distances. Uplands are inferred partly from absence. Erosion removes material from high ground and leaves thick sediment piles in adjacent low areas. The mountain itself may survive only in reduced form, or not at all, while the basin beside it keeps a voluminous record of what was stripped away. A missing body of rock can still shape the map through the deposits it supplied. Coarse fans, thick downstream sediment, and source-derived clasts all imply relief somewhere beyond the preserved section. In this way, absence becomes one of the most powerful signs of former elevation. Ancient lakes are recognized by combinations of fine laminations, shoreline deposits, freshwater fossils, and chemical signs of closed basins or seasonal drying. No single feature is enough. Fine layered mud may suggest quiet water, but with freshwater fossils and evidence of fluctuating chemistry, the setting settles more clearly into a lacustrine basin. Shoreline deposits mark the margins. Drying signs indicate changing water level. A closed basin leaves its own chemical imprint. Together, these clues define water held inland, separate from the sea, sometimes stable, sometimes shrinking and concentrating under seasonal or longer-term change. Restricted inland seas can be distinguished from open oceans when sediments show marine influence along with repeated evaporation, limited circulation, or unusual swings in salinity. They are marine but not fully open. Their waters connect imperfectly, and that imperfect connection leaves a mixed signal in the rocks. Fossils may show marine life, while chemistry and evaporite layers reveal confinement. Such basins occupy an intermediate place on the map, neither ordinary ocean shelf nor ordinary lake. Their margins can be broad, shallow, and changeable, and their internal conditions may vary strongly through time. Successive maps are made for different time slices because one region can shift from mountain front to river plain to shallow sea across millions of years. A single static picture cannot hold that sequence. The same crust passes through different climates, elevations, and water depths. Sediment that begins as debris near active relief may later lie under a floodplain, then under marine transgression. Each interval needs its own arrangement of coastlines, uplands, basins, and climatic zones. Paleogeography is therefore not one map, but a succession of maps, each resting on a narrow slice of deep time. Where evidence conflicts, multiple versions may remain in play, especially for older intervals where rocks are sparse or later tectonics has scrambled the record. One set of clues may suggest a peninsula. Another may fit an island arc or a broad shelf. When preservation is poor and deformation severe, certainty thins. The map does not always close. Some boundaries remain provisional. This is not a weakness in the landscape itself, but a consequence of incomplete survival. Ancient geography is partly erased by the same processes that create it: erosion, burial, collision, and recycling of crust. Uncertainty is often greatest along former coastlines and island arcs. These are places where erosion, sea level change, and later collision readily erase or distort the original geography. Coasts migrate. Sediment is reworked. Volcanic and tectonic activity complicate the record. Later suturing can break and stack the remnants. The result is a margin that may have been broad and intricate in life, but fragmentary in preservation. Even so, traces remain. A reef here, an offshore mud there, a volcanic sequence nearby, a restricted basin in between. The challenge is to let those fragments coexist without forcing them into false sharpness. As new cores and outcrops are added, boundaries are nudged, rotated, or redrawn. What had seemed to be a peninsula may become an island chain or a broad shelf. A basin once thought open may prove restricted. A source area may shift when new conglomerates or mineral matches appear. The map is therefore a layered synthesis rather than a fixed image. It combines ancient elevations, water depths, climates, and sediment pathways into one coherent landscape. But it remains revisable because the evidence itself is scattered, incomplete, and continually enlarged by newly recovered pieces. When many lines of evidence agree, vanished shorelines can be sketched with surprising clarity. Matching rock layers and fossils that now sit on continents separated by oceans begin to make sense within one older arrangement. A beach deposit on one block, offshore mud on another, a reef belt on a third, and a mountain seam crossing them all can settle into one continuous margin. The modern distances remain, but the older geography gathers itself. Fragments that seemed isolated become neighboring parts of the same coast, the same shelf, the same basin opening beneath the same sky. Ancient maps often show that a place now high and dry once lay beneath shallow water. Marine shells found far inland, ripple marks preserved in stone, and beds of salt within continental interiors cease to be anomalies once the older sea is restored. The land has risen, shifted, and been broken from its former setting, but the deposits still belong to water that once spread there. A dry plateau may carry the memory of a shelf sea. An interior basin may keep the chemistry of evaporation from a restricted marine arm. The map gives these inland traces their proper setting. Reconstructed uplands and basins also reveal where rivers likely flowed. Sediment pathways can be traced from eroded mountains toward vanished deltas and inland seas. Gravel fans near former relief pass into channel sands, floodplain muds, and finer basin deposits farther away. Conglomerates preserve pieces of the source. Sand minerals link distant receiving areas back to shared highlands. Once these relations are gathered into a coherent surface, the lost drainage network begins to appear. Water moves downslope again through the reconstruction, carrying the worn remains of mountains into low country and standing water. Climate belts placed onto ancient continents help explain why coal forms in some regions, desert dunes in others, and glacial scratches in still others at the same time. The contrast is no longer puzzling once latitude, tectonic position, and environmental indicators settle together. One part of a continent supports swampy lowlands where plant matter accumulates in waterlogged ground. Another carries oxidized red beds and dune sands in well-aired continental settings. Another records moving ice and cold debris. These differences coexist within the same interval because the continents themselves occupy varied positions and relief across the globe. Some ancient boundaries remain deliberately soft. Coastlines shift with tides, storms, and sea level change, and paleogeographic maps often show broad transition zones instead of sharp edges. This softness is faithful to the environments themselves. Deltas spread and retreat. Tidal flats are alternately wet and exposed. Estuaries mix fresh and marine waters. Barrier systems migrate. A line would imply a fixed certainty that the sediments do not support. The older world often consists of margins rather than borders, and the map rests more comfortably when it allows that breadth and movement to remain visible. As reconstructions improve, they can alter ideas about migration routes for animals and plants by showing when land bridges appear, narrow, or disappear. A corridor of exposed ground may connect regions for a time and then vanish beneath rising water. An island chain may replace what had been thought a continuous peninsula. A broad shelf may emerge where a barrier had once been assumed. The geography of movement depends on these details. Land and water do not simply occupy space. They open and close pathways across time, and the map records those changing passages. Ancient maps also test plate motion models, a reconstruction that places mountain belts, volcanic arcs, and seafloor remnants in sensible positions, carries more weight than one that leaves them misaligned. The fit must work across many kinds of evidence at once. Coastlines should agree with sediment transitions. Reef belts should occupy suitable shelves. Uplands should explain basin fills. Magnetic latitude, age constraints, and structural restoration should not pull in contradictory directions. When these parts support one another, the arrangement of moving crust becomes less abstract. It acquires terrain, water depth, climate, and sediment, and therefore greater coherence. Paleogeography gives Earth history a stage set. Isolated outcrops become parts of larger landscapes that once included bays, floodplains, reefs, deserts, and ice-covered margins. A coal seam belongs to a swampy lowland. A red bed belongs to arid continental ground. A salt deposit belongs to a restricted basin under strong evaporation. A limestone reef belongs to a warm, shallow shelf. The rocks do not remain as disconnected specimens. They settle into relation with one another, and the relation is the landscape itself, restored as far as the surviving evidence allows. Even the best reconstructions remain drafts. New drilling cores, new dating methods, and new fossil discoveries continue to adjust the picture. A boundary may shift. A terrain may find a different neighbor. A shelf may widen. A basin may prove younger or older than once thought. This revisability does not diminish the map. It belongs to the nature of the record, which is incomplete and uneven, preserved in fragments and altered by later history. The ancient world is approached through what remains, and what remains is always capable of yielding another connection. By assembling lost geography from scattered clues, different moments in deep time can be compared. Continents gather, split, flood, dry, and rearrange again. Seas spread across lowlands and withdraw. Mountains rise, shed their sediment, and wear away until only grains in younger basins preserve their memory. Reefs mark warm shelves, salt marks restricted water, coal marks wet low ground, ice marks cold passage. Across all of it, the rocks continue to hold pieces of worlds no longer present as surfaces, but still present as structure, texture, chemistry, fossil, and age. In the end, the ancient map is never a return of the whole earth as it once stood. It is a careful joining of fragments into a landscape that can hold coastlines, uplands, basins, climates, and pathways together without forcing them beyond the evidence. Some margins remain open, some seas stay broad and uncertain at their edges. Some highlands are known mainly by what they have shed and lost. Yet the reconstruction still settles into coherence. Broken pieces of crust, scattered sediments, and faint magnetic traces come to rest in one quiet arrangement where former bays, river plains, reefs, deserts, and ice-worn margins lie once more in relation, and deep time becomes a sequence of connected worlds. The old landscapes do not arrive all at once. They rest in pieces. A band of sandstone here, a seam of coal there, a reef turned to limestone, mud laid down in quiet water, gravel dropped by a stronger flow. Each piece keeps a little of its first place, even after burial, even after erosion, even after the long carrying of crust across the globe. A continent in the present is not one unbroken thing. It is a collage, joined edges, welded fragments, pieces that once belonged to other settings, other latitudes, other shorelines. In each piece, some small part of an older world remains. A surface once touched by rain, a ripple once moved by waves, a bed of salt left where water thinned under heat, a burrow where life worked through soft sediment and left its quiet mark. So the lost map begins low to the ground, not with borders, not with names, with grain, with texture, with the tilt of a layer, coarse gravel near a steep source, fine mud settling where water is calmer, sand arranged by current or wind into slanting lines within the rock, mud cracks opening and drying at the surface, then held there for ages in stone, raindrop pits, ripple marks, small records of air and water meeting the earth for a moment, then passing. Fossils rest among these signs, corals in warm, shallow seas, pollen washed in from nearby forests, tiny shells that speak softly of depth, salinity, or temperature. Chemistry lingers too. Fresh water, brackish water, waters made saltier still by evaporation in a restricted basin. None of these clues stands alone for long. They gather, they overlap, they lean toward one another until a place begins to appear. And always there is time. A shoreline from one age can look into another if the dates are loose. So the layers must be held in order, some by fossils, some by ash fallen thin across a wide region, some by lava or ash dated more firmly, some by the faint magnetic memory kept in rock. Only then can the fragments begin to sit beside one another in peace. The rock layers rise in stacks and packages. One setting gives way to another. Sand above mud, limestone beside shale, a beach passing outward into offshore quiet, a river plain broadening and then sinking under shallow sea. These changes do not hurry. They spread upward through the section, sideways through the basin, and outward across distances now broken by faulting, folding, and time. Nearby outcrops answer one another across valleys and ridges. A sandstone in one place becomes mudstone in another. A limestone shelf thins and disappears. A coal seam holds its dark line through the low ground. Local slices begin to join. The wider picture forms slowly, as if lit by a lamp turned up only a little at a time. Where beach sand grades seaward into offshore mud, an old coastline leans into view. Land on one side, deeper water on the other, more often a broad shifting margin, deltas spreading outward, tidal flats drying and flooding, estuaries mixing fresh and salt water, barrier systems lying low along the shore. The boundary between land and sea widens and softens there. Inside the sand, the tilted layers of crossbeds keep the memory of movement. Dunes once advanced, currents once pressed in one direction more than another. Ripple marks hold their own smaller language. Some are shaped by waves moving back and forth, some by a steadier current. The stone keeps both motions, the brief trembling of water, the longer push of flow. Mud cracks open another scene, wet sediment drying, a surface exposed, then covered again, a tidal flat, a floodplain margin, the edge of a lake in a season of retreat. These are places where water comes and goes, places of shallowness, of return. Fossil shells must rest carefully in this quiet world. Some live where they are found. Some are carried there later by storms or stronger water. Tiny fossils often speak more steadily, a narrow range of depth, a narrow range of salinity, a narrow range of warmth, so small and yet so exact in the conditions they once needed. Pollen and spores drift in from nearby land and settle into the record. They suggest wetlands, forests, or drier interiors beyond the outcrop itself. Coal marks another low country, long-lived swampy ground. Plant matter gathering faster than it fades in waterlogged stillness. A dark layer left by a broad and persistent softness of land. Elsewhere, thick beds of salt or gypsum lie where water once stood in restricted basins and evaporated again and again. The sea was near, perhaps, but not fully open. Circulation narrowed. Salinity rose and fell. A shallow water body remained under a strong sky, shrinking, returning, shrinking once more. Limestone reefs trace warm, sunlit shelves. Broad, shallow platforms along the edges of ancient seas. Their presence steadies the map. Their shape suggests where open water begins and where the shelf once lay. Far from them, red beds spread across continental settings, iron-stained and aired, more at home on floodplains or in deserts than under deep marine water. In colder chapters, the signs change. Glacial scratches cross stone. Poorly sorted debris lies where moving ice leaves it behind. The direction of that motion can still be read in places. A cold landscape enters the reconstruction, marked into rock by pressure and passage. Ancient rivers gather from many clues at once. Channel sands, floodplain muds, gravel fans spread outward from older uplands. Conglomerates hold large rounded pebbles, energetic enough to have been carried by swift rivers or rough shorelines. And the pebbles themselves remember their source. Their rock types point back toward vanished highlands that may no longer stand anywhere at all, except as scattered grains in younger basins. Durable minerals and sand grains travel with that memory too. Separated basins can still share the same source terrain, and the grains quietly show it. One basin answers another. One fragment of continent answers a fragment far away. Sediment pathways extend from eroded mountains toward lower country, toward deltas, toward inland seas now gone. Thin ash layers settle over all of this like pale time marks. A single eruption spreads fine material widely. Distant sections can be aligned by that brief fall from the sky. Radiometric dates anchor some of those moments more firmly. Magnetic signatures narrow others, holding both age and latitude in a faint record. Then climate signs can be set beside position. Tropical reefs, desert dunes, glacial deposits, each more at ease in some belts than in others. But the rocks do not always remain where they were first laid down. Later deformation bends them, breaks them, stacks them. Faults shift packages apart. Folds lift and turn what was once simpler. So the layers are restored as much as they can be, eased back toward flatter beginnings, toward a calmer arrangement beneath the later strain. Terrains carry their own separate histories, distinct fossils, distinct ages, distinct structures, distinct igneous activity. They are matched to likely neighbors with patience. Mountain belts on one modern continent can line up with belts on another when the continents are turned backward through time. Long seams appear across present oceans. Old joins, old sutures, edges that once met and then drifted apart. Some of this turning backward is guided by seafloor spreading histories, though only where the ocean floor is young enough to remain. Older oceanic crust is often gone, returned to the mantle. So the lost geography is never complete. Some evidence is absent from the beginning, some is erased later, some lies too altered to speak clearly now. Even so, maps begin to gather shape. Continental blocks are placed, rotated, nudged. Their positions are tested against field evidence, not replaced by models. Shorelines are drawn lightly, because shorelines themselves are light-footed things. They shift with tides, with storms, with sea level rise and fall. A region may pass from dry land to shoreline to shallow sea to deeper water, then back again in another age. No single crisp line can hold all of that motion. Uplands are often known by what is missing. High ground loses material, low ground receives it. Thick sediment piles collect in adjacent basins while the source is worn down. So a vanished mountain range may survive only in the outward spread of its debris. A summit gone, a slope gone, but its gravel remains, its sand remains, its minerals remain. The basin keeps what the highland has surrendered. Ancient lakes appear where fine laminations, shoreline deposits, freshwater fossils, and chemical signs of closed basins gather together. Some dry seasonally, some deepen, some contract and leave a sharper chemical trace. Restricted inland seas hold a different balance, with marine influence still present but circulation limited, salinity changing, evaporation returning again and again. And because one map cannot contain all time, many maps are made, one slice after another. A mountain front in one interval, a river plain in the next, a shallow sea later on, the same region changing character over millions of years, flooded, dried, buried, lifted, rearranged. Sometimes the clues agree and the landscape settles. Matching rock layers and fossils sit on continents now far apart, yet the vanished shoreline between them becomes easier to sketch. A place now high and dry is understood to have once lain beneath shallow water. Marine shells far inland become less strange. Ripple marks on a plateau grow quieter in their explanation. Salt deposits in the interior return to their old basin. Sometimes the clues do not agree. Then more than one version remains alive. This is especially true in older intervals, where rocks are sparse, or along former coastlines and island arcs, where erosion, sea level change, and later collision leave the geography blurred. Boundaries stay fuzzy there. A peninsula may become an island chain. A shelf may broaden. A line may move a little with each new core, each new outcrop, each new comparison. In the end, the reconstruction rests as a layered landscape. Ancient elevations, water depths, climate belts, sediment pathways, bays, floodplains, reefs, deserts, ice-marked margins. Many clues lie over one another until a coherent world appears for a while. It remains a careful draft. New cores may shift a boundary. New dates may quiet one uncertainty and open another. Fossil found in the right layer may turn a coastline, or narrow an inland sea, or place a terrain beside a different neighbor. The map is never final. It stays gentle at the edges, revisable, patient, true enough to hold and loose enough to change. Still, the larger motion endures. Continents gather and split. Shorelines advance and withdraw. Uplands rise and wear away. Rivers cross lowlands toward basins that later vanish. Reefs grow in warm shallows. Salt settles in restricted water. Cold darkens in swampy ground. Ice scratches stone and moves on. Then all of it is broken, buried, scattered, and found again in fragments. From those fragments, the old world returns in outline, quiet and incomplete, like a coast appearing through mist. And the rocks continue to keep their small pieces of place. A ripple under stone, a grain from a vanished mountain, a shell from shallow water now lifted far inland, a thin ash line crossing distance, a seam of coal marking a long wet lowland. They remain where they can, through folding and faulting, through loss and rearrangement, holding enough for the land to be drawn once more, softly, in the dim and patient light of deep time.